You are spotlighted. And
He's trying to do it now, I think.
Val, I'm just going to make you host.
Oh, okay. Okay, we're in business.
You're ready, Alan.
I can start. Okay, are we ready to start?
Yes.
Okay. Wow, what a production. I would think we were actually going into space. It's amazing with this technology. Well, hi, everybody. Thanks for joining me today. And what a good turnout. My name is Alan Russo. I work at the Eastern Chatham Senior Center, and my background is environmental education, and I really enjoy doing these science programs whenever I get the chance. Makes me think about the things I used to do a lot. And you know, you've heard the saying, if you don't use it, you lose it. So sometimes it's good to do these just over and over again, because I just need to remind myself of what I used to know. So what we're going to do today is we're going to talk about space, and mostly about our solar system, but we're going to go beyond the solar system a little bit and talk about, you know, distances and light and things like that. And I did have one request. It was from Kay about the moon and how the moon causes the tides. So I actually found it's kind of hard to explain when you're not there in front of a person with a blackboard. So what I did was I found an interesting video that I think might help explain. And I really would rather this be a discussion than a lecture. So if anyone at any point has any questions about what I'm talking about, because I know a lot of this stuff is a little, you know, no pun intended, but far out there, you know, as far as the numbers and distances and stuff like that. So anytime you have a question, just jump in. And for the people who are just on the phone, I'm going to try to explain the slides when they come up. And let me just jump over to the slides. Click on that. From the beginning. Okay. All right, can everybody see that?
Yes.
Yes.
Good, okay. So now a lot of the things I'm going to talk about right now, especially in this part of the talk, it's what's known as a theory, because obviously nobody was there to witness what happened, but based on all the observations and the science behind it all, scientists have a pretty good idea by watching what's going on in the universe right now on how our solar system formed. So our solar system and our star are at least a second generation star. And what that means is that another star had exploded, and all that gas and dust that went out into space eventually condensed into our solar system. Now, the way they know that is because when they look at young stars, first forming stars through a telescope, and they use this special tool to tell what the star is made of, they could see that our star actually has heavy metals in it, like iron and gold and silver and all these things. In a brand new star that never, you know, that just formed from just gas, you won't get those heavy metals. The only way you can get heavy metals is from a star that's been around a really, really long time and has supernova or exploded and shot out all of those big heavy metals out into the solar system. So the fact that our sun, being so young, has all these heavy metals, scientists basically deduced the fact that our sun is at least a second generation star, if not a third generation. So imagine that, a star had to go through its life of billions of years, finally reach the end of its life and explode, and all that gas, dust, and rocks, and of course all the planets that were around it vaporized, went out into space. And the most important force in the universe to form the solar system and everything else in the universe is gravity. Now, gravity is strongest based on the size of an object. I shouldn't say size, I should say the mass of an object. So the mass of an object determines how much gravity it has. In gravitation, gravity is a pull. So imagine billions and billions and billions and billions and billions of tons of matter out there in space. It starts to pull in on itself and starts to spin because things didn't come in from each side equally. So the one, like a bunch of stuff comes in from one end and it starts to spin. And when that happens, it starts to form a disk. And that's what we call the planetary disks, which is you'll always find the planet on that line, which is called the ecliptic. So this slide kind of shows a little bit about what the very early solar system may have looked like. Just a big giant disk of dust, and big clumps of dust started to come together and starting. Now imagine this, you have two rocks come together. So now they have twice the amount of gravity. So they start pulling in other rocks, and the more stuff they pull in, the more dust and gas they pull in, the more gravity. So the more gravity, the more stuff they pull in, and eventually, that we can call a planet. Any questions? So in our solar, we have the sun, which is the thing way on the left. We have Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. Now, when I was a kid, I learned that Pluto was a planet, and in my mind, Pluto will always be a planet. And I think that just because you change the definition of something doesn't mean you should degrade it all the time. So it turns out that Pluto is not considered a planet now. It's called a planetoid. It's a small planet. And we'll get into that in a minute when we get to Pluto, okay? So there are planets. Now this picture that you see is really deceiving. What it's really just trying to show is the relative size of the planets and where they are in line away from the sun. Obviously, the planets are not this close together. You know, some planets are closer, some are further away, and so on. So at the very center of our solar system is the sun. And the sun is called Sol. And that's an ancient term for the sun. And that's why everything that has to do with the sun is solar, or Sol, S-O-L-A-R. So it's the solar system, it's the system of Sol. You know, when we talk about solar energy, we're talking about energy coming from Sol or from the sun. Anything that has to do with the sun is usually starts with the S-O-L, which is an ancient term. Now the sun is huge. And here's some facts about the sun. Let me see something. Hey guys, how do I get rid of the pictures, people's faces on the right side of my screen?
Click on your
Anybody
view
know?
in the upper right corner.
All right, there's nothing that says view.
Oh,
It says your screen is shared. All right, it's probably because I'm on the shared screen. All right, I think I could probably figure this out. Well, it's just covering up some of the words. Anyway, you guys can see it. So the sun is all the colors of the rainbow mixed together, which means it appears white to our eyes. Now, the other thing I was going to talk about when I talked to Kay, she was like, well, you know, let's talk a little bit about light. So the light that comes from our star is considered white light. Now, if you run that light through a spectrum or like a prism, you know, some people put these things in their windows that are made of glass, and then it shoots this rainbow out onto the walls. Well, all those colors are actually in that white light coming from the sun, and it's not till it passes through certain kinds of mediums that it breaks apart into the different colors. And those colors are different frequencies. Now, you could always remember the colors of the rainbow. I remember in school they taught us this little abbreviation. It's called Roy G. Biv, almost like it's a person's name. So Roy would be red, orange, yellow. Roy G, I'm sorry, green. And BIV would be blue, indigo, violet, IVE. What did I miss? BIV. Yeah, where's your BIV? Violet, okay. So all of those different colors are actually different frequencies of light. And we see the colors of the rainbow, what we call the visible spectrum from the sun. Now, there's lots of other stuff coming from the sun, and that whole thing is called the electromagnetic spectrum. But our eyes can't see all the things that are coming from the sun. Like we can't see X-rays or gamma rays or radio waves. But there are certain animals who can see things differently than we do. For instance, a bee, when it looks at a flower, the flower doesn't look anything like it does to us because they can see different frequencies of light than we can. Does that make sense?
Yeah.
It's a little complicated, but I think the whole idea of light is just amazing because, you know, when you look at somebody's clothes, for instance, or you look at the color of their skin, what you're looking at is that, let's say I'm wearing a red shirt. You're looking at the light that's being reflected back into your eye. So this person's shirt is actually absorbing all the colors of the rainbow except for one. It's reflecting light back, the red light. So that's the part that's reaching your eye so you can see it as red. Now, if somebody's wearing blue jeans, your jeans are actually absorbing all the colors of the rainbow except for the blue. The blue is actually being reflected back out into space, and you see it that way. So when you're looking at something, you say, oh, it's red. It's really not red. It's just reflecting red. So that's a really interesting concept. You know, when you look at the sky and the sky looks blue, the sky's not really blue. It's just doing all this stuff to light so you can see the blue spectrum. Okay. Now the sun is mostly composed of hydrogen and helium. You can see 70% and helium 28%. And we don't need to get into the sequence. The sun is 109 times wider than the Earth and 330 times as massive. So I read one time that you could actually fit 100,000 Earths in our sun. The sun's surface is about 11,990 times that of the Earth's surface. Now, the distance between the Earth and the sun, now this is a mean distance because it averages. We go around the sun. It's not a perfectly circular orbit. It's actually slightly elliptical. So sometimes we're actually closer to the sun and sometimes we're further away. The mean distance is 93 million miles. And that's something called an astronomical unit. A lot of times you'll read something on, on space and they'll say, well, the comet will be within 3 astronomical units of the Earth. And people are like, what does that mean? Why don't they just tell us miles? Well, astronomical units says 3 times the distance of the Earth to the sun. So you know what that is now. The sun is traveling at 220 kilometers per second. One day the sun will eventually consume the Earth. Don't worry about it. It's not going to happen anytime soon. They're thinking about 10 billion years. So what's happening is a star, like our sun, actually goes through a life cycle. It's born. It's very energetic, just like a teenager. Eventually, it slows down and it gets a little bit bigger, like a lot of our bellies when we get older. And it starts to enlarge and get bigger and bigger and bigger till eventually scientists believe that it's going to become a red giant and will actually consume the Earth. The sun will actually be as big as the orbit of the Earth and maybe even beyond. Okay? The temperatures inside the sun can reach 15 million degrees Celsius. I'm not really sure what that is in Fahrenheit, but it's a lot more than that. So, I used to tell kids, like, you can't imagine, like, the sun is 93 million miles away from us, but it can still burn you. And they're like, what? You're gonna go, like, what, do you ever go to the beach and get a sunburn? Well, this is an object that's so hot, it's 93 million miles away, and it could still burn your skin. That's pretty amazing if you think about it.
Yes, it is.
So the very first planet, now, I'm just going to give you this basic overview. The rocky planets are closer to the sun, and the gaseous planets are further out. I'm not 100% sure why, and I don't know that scientists know the answer, but when you think about something as far as density goes, how heavy something is, something that's heavy, like rock, gets pulled in closer and faster to the object than gas would. So all the planets that are closer to the sun than we are called inferior planets. Not that they're inferior, like less important, but inferior meaning closer or closer to than we are. Okay, so Mercury is the closest planet to the sun. The other thing you need to know about planets is the planets that are close to the sun actually go around the sun much more quickly than the ones further out. So a couple of things about Mercury. It doesn't have any moons or rings. Mercury is the smallest planet. It's the closest planet to the sun. Your weight on Mercury would be 38% of your weight on Earth. So you could actually go online and find these calculators. Okay, did you have a question?
No, I was saying yay.
Oh, okay, I thought you were waving. I'm sorry. So
Yeah.
remember I said the mass, something that gravity has to do with the mass of an object? If something is smaller, it has less gravitational pull. So the only reason why you weigh what you do is because the amount of gravitational pull on the Earth. If I put you on the moon, which is much, much smaller than the Earth, you're going to weigh a lot less. So you actually don't weigh anything. What you weigh is based on the amount of gravitational pull that you have on you. So because Mercury is so small, if you went to Mercury, if let's say you weighed 100 pounds, if you were on Mercury, you would only weigh 38 pounds. Okay? Now, a solar day on the surface of Mercury lasts 176 Earth days. Now, a day is calculated based on how long it takes the planet to rotate once. So our Earth, for instance, has a 24-hour day. It takes 24 hours for our Earth to rotate once on its axis. Some planets move faster, some move slower. It just so happens, even though Mercury is smaller than the sun, it's slow in its rotation. One day on Mercury is 176 Earth days. So imagine you're out there getting a suntan. You talk about suntan, right? So whatever half of 176 is, that's how long the day is. And of course, half of that would be how long the night is. So the night would be, 90, what is it, 9 and 18? So it's like 80 something Earth days would
I
be
do
one
have
day.
a question.
Yes.
When I lived in Iceland, sometimes it was dark 24 hours a day, and sometimes it was light 24 hours a day. Does that have something to do with what you're talking about?
Nope, not at all, actually, because the Earth, let's assume that the Earth's rotation is constant, which means it rotates once in 24 hours, correct?
Right.
What causes the days to be longer in the in the summertime up north is actually the tilt of the axis of the Earth. Now, when we talked about the seasons and how the seasons occur, I talked a lot about that. So what happens is in the summertime, the northern hemisphere is actually pointed towards the sun. So if you go to the North Pole, the sun never sets. Now in the wintertime, here's the sun. The Earth's axis is actually tilted away, which means the North Pole doesn't get any sun, which means it gets 24 hours of darkness. So as the sun goes, as the seasons move on, it changes. So that's what that has to do with.
Okay, thank you.
So here's the thing. A year is how long it takes a planet to go around its star. Now for us, we'll talk about this later, but for us, it takes about 364 point something days for us to go all the way around the sun, right? So that's 1 year. Well, a year on other planets is completely different. A year on Mercury takes 88 Earth days. That means every 88 days equals 1 year on Mercury. Now, remember I said the closer the planet is to the sun, the quicker it goes around it. So obviously, if Mercury's going around the sun a lot faster, its year is going to be shorter. Does that make sense?
Mm-hmm.
Okay. All right, let's jump up to the next planet. So this one, anybody know what the next planet is after Mercury?
It's not, is it Venus
All right,
or
I'll give it to you.
Venus.
Venus, yeah.
Venus.
Now, here's an interesting thing. Okay, let's just go through these. Venus does not have any moons or rings. Venus is nearly as big as the Earth. It's a little bit smaller. Venus is thought to be made up of central iron core, rocky mantle, and silicate crust. Not that important. I'm not going to go through every single one of these. A day on the surface of Venus, or a solar day, would appear to take 117 Earth days. In other words, it's spinning a lot slower than the Earth is. Now, a year on Venus takes 225 Earth days. So it's basically cruising around the sun, just like Mercury is, right? Now, the surface temperature on Venus can reach 471 degrees Celsius. Now, you would think that Mercury would be the hottest planet because it's closer to the sun. Well, it turns out that Mercury barely has any kind of an atmosphere, but Venus has a very thick carbon dioxide and sulfur dioxide atmosphere. Both of those gases are what are known as greenhouse gases. Now, you've heard about the Earth getting warmer because we're putting so much carbon dioxide into the atmosphere. So it works as a greenhouse gas. Well, think about Venus as the greenhouse effect gone wild, because there's so much greenhouse gas that it traps the heat from the sun, where the temperature goes up to 471 degrees Celsius. That's hot enough to melt lead, by the way. So scientists have a real problem trying to find out what's going on the surface of on Venus, because one, you can't see through those clouds of sulfur dioxide, and two, if you send a probe, it's only going to last a few minutes. If you're lucky, 15 minutes, or else it'll just melt. So they don't really have a lot of real definitive, pictures of what's going on in Venus. And here's my favorite planet. I'm not too biased just because I live here or anything like that, but of course the Earth. And one thing you'll notice about the Earth is very colorful compared to the other. It's different color than the other planets. Well, a lot of people, scientists actually dubbed this the blue marble, because when the first time they saw it from the moon, the full Earth rise, it looked like a beautiful blue marble out there in space, just rising above the horizon of the moon. Now, the Earth is unique in so many different ways. It could take hours to actually talk about this. So the Earth formed about 4.5 billion years ago. So that's how old the scientists believe that the solar system is, approximately. Of course, they're not sure 100%. And like I said, nobody was there. So planet Earth is the third closest, and it is a rocky planet. So a lot of times we call it the third rock from the sun. Earth is the fifth largest planet in the solar system. The radius of the Earth, well, let's not even talk about the radius. Let's talk about the diameter. I'm sorry, the circumference. The circumference of the Earth at the equator is approximately 24,000 miles. Now, our day just happens to be 24 hours long, which means we move every hour. Our Earth is spinning at about 1,000 miles an hour. Now, Earth's closest distance, which is called perihelion, is 91 million miles. Aphelion is the furthest distance, which is 94,000. So the mean distance, before I was telling you, one astronomical unit is about 93 million miles. It takes one Earth year or about 365.256 days to complete an orbit around the sun. Now, you might not think putting that 2.256 at the end of the 365 is not important, but as the years go on, that 0.256 days actually adds up. So a long time ago, people figured out that it wasn't exactly 365 days. To keep the calendar in check, they actually had to add an extra day onto the calendar once every 4 years. And we know that that happens, and we call that leap year, right? That's to keep the calendar. Now, the Earth has one moon, and a moon is called a satellite. The satellite of the Earth, one natural satellite, is we call it the moon. The Earth's moon is over 238,000 miles away, and the Earth's shape is an oval-shaped ellipse. Now, you might think the Earth is a perfect sphere, but we know the Earth is spinning, and we know it's really heavy, and we also know that it's not 100% solid. So when you spin something, what's going to happen is called centripetal force, actually pushes out the center of the Earth. So at the equator, it's actually bigger, it bulges a little bit more than the poles. So it's actually longer to go around the equator than it would be to go around from pole to pole on the Earth. It's not a lot, but it's noticeable. All right, we don't need to get into the geology. One thing that's unique about the Earth is it has an atmosphere. And the atmosphere is mostly nitrogen, it has oxygen, and it has lots of other gases. Now, we call that air. When you put all those gases together, we call it air. And, you know, the atmosphere on the Earth is different now than it was, say, 100,000 years ago, or 2,000, or a billion years ago. You know, if I could transport you in time back 500,000 years, or say a billion years, you would get out of your spaceship and you'd die as soon as you stepped out onto the Earth. You couldn't breathe the atmosphere that it was. And it wasn't until plants started to come onto the scene and produce oxygen that we got all this oxygen in the atmosphere, okay? And of course, the most important thing, Earth is the only planet in the solar system known to harbor life, now or in the past. So, like right now, we're doing all these surveys of Mars, because we know that Mars used to have a lot of water, and we know that water is a really important part of life. In other words, you don't have any light, you don't have any water, you don't have life, period. So the fact that Mars had lots of water on it, scientists think that maybe life even started up on Mars. So they're spending a lot of time and a lot of money looking for signs of life on Mars. Haven't found any yet, so still at this point, as far as we know, we're the only planet in the solar system that has life now or ever had life, okay? And the most important thing to life, of course, like I said, is water. And about 70% of the Earth's surface is covered with water. Now, we're not going to get into water too much because I could talk for an hour on water. It's just so cool. It turns out that only 3% of that water that you see on the Earth is fresh water. And most of the fresh water is not even available to us. There's lots of fresh water in the clouds. There's lots of fresh water in the atmosphere. There's lots of fresh water underground. We can't get to that, most of it. So only about 1% of the water on the Earth is actually usable to animals and plants. Okay. Any questions about Earth?
When will we be able to talk about the tides at a different time?
No, we're going to get to that in a minute. We're going to get to
Okay,
that in a minute.
okay.
Talking about life.
So this is interesting. You know, I'm sitting here at my computer. I don't feel like I'm moving at all. I'm sure that you don't feel like you're moving. You know, we stand on the Earth, we walk around, we don't even notice what's happening. But I find this really interesting, and I thought I'd share it with you. The Earth rotates once every 23 hours, 56 minutes, right? Which means, and the circumference of the Earth is roughly 40,075 kilometers. Thus, the surface of the Earth at the equator moves at roughly 1,000 miles an hour, as I said before. But not only is the Earth spinning, but the Earth is actually going around the sun. So the Earth is actually going around the sun at 67,000 miles per hour. So not only are we spinning at 1,000 miles an hour, we're traveling through space around the sun at 67,000 miles per hour. In addition, our solar system, Earth and all, whirls around the center of our galaxy at over 490,000 miles per hour. So let's add that up. Let's see, we got 67,000 miles per hour, plus 1,000 miles, plus 490,000 miles per hour. So that's just the Earth movement within the galaxy. Now, our galaxy is actually moving out in space at over 1,000 kilometers per second. So we are going so fast that you can't even imagine the speed we're moving through space right now. So you might ask yourself, why is it that it doesn't feel like we're moving at all? Well, think about this. When you're in a car and you're doing 70 miles an hour, if there were no windows in the car and your car was like a really good car and it was really smooth, you were on a road that wasn't bumpy, you wouldn't know you were moving because everything inside your car is moving the same speed that you are, right? It's not till you look out the window and you see trees whizzing by that you know that you're moving quickly. So same thing on Earth. Think about the Earth as a car that we're in or on. We are moving at the same speed the Earth is, so it doesn't seem like we're moving at all. But when you look out into space and you look at the stars at night, for instance, you'll go outside and you look at, say, Orion. And then you go out 2 hours later, you'll see, oh, look, Orion's in a different spot. Like, how did that happen? That happened because the Earth is in constant motion. So we're really whipping through space at speeds that are just mind-boggling right now. Now, here's somebody wrote this thing like, what if the Earth just stopped instantly? If the Earth just stopped instantly, two things would happen. You'd go flying off the Earth because it'd be just like, imagine if you were sitting on the hood of a car and somebody hit the brakes, you'd keep going because you're not actually attached to the car. We're not actually attached to the Earth. So if the Earth actually stopped instantly, you'd go flying off the Earth. The other thing that would happen is the atmosphere would keep on moving, which means the winds would be thousands of miles an hour if you were able to stay on the Earth, since the atmosphere would be moving, okay? So I'm going to talk about the moon real quick, and we're not going to get into the whole how did the moon form and all of that, but I'm throwing this in there because Kay had asked, and we have one satellite, we call it Luna, or the moon, okay? The moon is constantly moving around the Earth. We always see the same side of the moon because the orbit and the rotation are equal. So it rotates once for every orbit that it goes around the Earth, so we're always seeing the same face. Now, it does move further away sometimes, and it does move closer sometimes. And when it gets closer, there's more of a gravitational pull, and when it's further away, there's less, but it's hardly noticeable. So because it's really hard to explain the tides without being in person with you guys, I found a video that actually explains it pretty well. Okay, so I'm going to show that to you right now. Hopefully it comes up as a play. Wait, where's the play button? Uh-oh. Hold on, guys.
Looks like it's
For
in the
some reason,
lower
the
part
play
of the
button's
screen.
not happening. Oops. I'm not seeing it. It should be right in the center.
It's at what I see on the slide is at the bottom.
The bottom on the left.
All right, there we go. There we go. Thank you. So this is my internet connection is unstable. So this might not work as well as I hoped. All right, I'm gonna actually go find the video if this doesn't work. Oh, there we go, okay.
This shows 12 hours at the famous Bay of Fundy in Nova Scotia, Canada. It's the biggest tide change in the world. But what force could move such a massive body of water?
By the way, guys, if you've never been to Nova Scotia and you have never seen the Bay of Fundy, this is really very cool, because you'll get there in the morning or sometime of the day and all these boats will just be laying in the mud. And 6 hours later, the tide is up where they could actually go out fishing. So if you live in a place like the Bay of Fundy and you're a fisherman, your life revolves around the tides. And of course, if you're out fishing and you have to come back, you can't just come back. You have to come back when the tides say that you can come back. And tides in some places in the Bay of Fundy are 50 feet difference between low tide and high tide. For comparison, where I used to live on Long Island, it's 8 feet, the difference between high tide and low tide. Okay, so there's a really big change. So let's get to why that happens.
Gravity. Here's the Earth rotating on its axis every 24 hours.
Can you guys hear that?
No, not well.
No.
So you're going to have to turn up the speaker on your computer.
Mine's up.
With its surrounding layer of ocean. And to the right is the silvery moon.
I can't hear it.
Everything is attracted to everything else in the universe with the force of gravity. So the moon is attracted to the Earth. And the Earth is equally attracted to the moon.
I can't
Notice
hear
that
it.
the two force arrows are the same length, showing that gravitational attractions are of equal strength. But we're only interested in the force on the Earth here. The moon pulls on the ocean closest to it and makes it bulge outwards. When the Earth rotates, the sea level is high in its rotation, called high tide. And low tide where the oceans don't bulge. So you expect one high tide each day. But here it gets interesting because there are 2 high tides a day. How come? This is because the strength of gravity is greater when objects are closer. We'll call the location of the ocean on the near side of the moon point A, at the center of the Earth point B, and at the far side ocean point C. The strength of the moon's gravity is strongest at A because it's closest to the moon. So the part of the ocean that bulges towards the moon most is at A. But the moon's gravity also pulls on the Earth, moving it towards the moon as well. This has 2 effects. First, it makes another bulge at C. Second, it fills in the bulge at A, but not completely, because A has moved further towards the moon than B. Lastly, the far side ocean at sea is also attracted to the moon, but it moves least because the moon's gravitational pull here is at its weakest, being...
All right, guys, I'm just going to jump ahead. That's a little complicated. But I do want to show you what that actually... So, remember I said, briefly, I said that every 6 hours the tide goes in and out, goes in or out. So if you were a fisherman in Nova Scotia, you'd have to wait at least 6 hours to come back in before you can, for the tide to be high. Now, if there was only one bulge of water on the side of the Earth where the moon is, we'd only get one high tide because this next... So there's a person right now when the Earth spins around to that point, that person at the beach, it's low tide. But look at this, 6 hours later, as the Earth rotates, now it's in the bulge on the opposite side of the Earth. So it's high tide, which is 6 hours later because it takes 24 hours, and divide that by 4, it's 6 hours. Another 6 hours goes by. Now we're in low tide again. And again, 6 hours later, we're in high tide.
Through 2 high tides and 2 low tides.
All right, any questions on that?
I heard
So that's-
about half of it, but it was very interesting. Yes, I'd never seen it that way.
Yeah, and of course, remember I said gravity has to do with everything in the solar system and in the universe, pulls things together. By the way, I don't know if you realize this, but remember I said anything that has mass has gravity. The higher the mass, the more gravity. You have gravity. I have gravity. Only we're so small compared to the Earth that the gravity is not enough to attract us to each other, or to the Earth, for instance. You know, right now we're being pulled right center of the Earth. But lucky for us, the ground is in the way. And we don't go to the center of the Earth. And I used to tell kids, I was like, I can prove that to you. All you have to do is jump off a cliff. If you jump off a cliff, you're going to get pulled towards the center of the Earth until the Earth gets in the way again. And then, remember the old saying is, it's not the fall that kills you, it's the sudden stop at the end. Well, imagine if there was a hole deep enough. This is interesting too. Imagine if there was a hole that went right through the Earth, right through the center of the Earth to the other side. If you jumped in that hole, you'd get sucked towards the center of the Earth, and you would pick up speed the closer you got to the center of the Earth. That you would not actually stop at the center of the Earth because you'd have momentum. You'd actually go past. But you wouldn't have enough momentum to get you past to the other side. So you'd start to get pulled back and forth. You get pulled back and forth, who knows, maybe 100 times before you finally settled down into the center of the Earth. So I hope that explains a little bit about the tides. Now,
So,
wait, why is this not going for? There we go. Now, the other thing I want to say about the tides, you know, not only is the moon pulling on the Earth, but so is the sun. So when the moon is on this side of the Earth and the sun is on this side of the Earth, those two tides are accentuated. You get these two high tides, or spring tides, they call them. Now, when the moon is on the same side of the sun, it actually exaggerates the high tide even more, because now you got the moon and the sun's gravity pulling the water. So when I said, you know, on Long Island where I used to live, that the tides were 8 feet in difference, that's only at certain times of the month. It changes constantly because the moon is constantly going around the sun, and the gravitational pull is changing. Okay. Oops. Sorry. So now we're done with the inferior planets, and we're going to start to head out into space a little bit. And the next rocky planet out there is Mars. Now, we call Mars the red planet, and if you've ever seen any pictures that were taken by the spacecraft that are up there, it looks pretty red. And the reason it's red is there's a lot of iron, and when iron oxidizes or rusts, it looks like rust, basically, the color of rust. So let's see, equatorial diameter, or let's see, it's smaller than the Earth, so it's 0.11 Earth masses. It has 2 moons, and let's see, the ordered period, okay, it takes 1.9 of our years but Mars to go around the sun, which means the year is longer than it is here on Earth. And as we get further out into the solar system, you'll see that it takes longer and longer for planets to go around the sun. Now, the temperature is very cold, -87 to -5. The reason there's such a fluctuation is because in the sun, it's a lot warmer. Now, Mars does have an atmosphere, but let's take the moon, for instance. The moon doesn't have an atmosphere. If you went on the moon and you were in the sun, it might be 287 degrees. If you stepped into the shade 5 feet away, it would be minus 200 degrees. Because there's no atmosphere regulating the temperature, like here on Earth, you will get instant changes. Now that line between sun and shade is called the terminator. When you look up at the moon, you only see half the moon lit up. That line is called the terminator. It's called the terminator on all planets. But Mars does have an atmosphere. So there would be a gradual change from cold to hot when you go into the shade on Mars. It wouldn't be instant like that, okay? And, you know, again, we're up there on Mars looking for the signs of life. Who knows what they're going to find? Now we're going to get giants, so the gaseous planets. As you get further away from the sun, you start to get into more gas. This is the largest planet in the solar system. We know it as Jupiter. And all those, let me go back a second. All those different colors, the different bands, those are all cloud layers made of different kinds of gas. So those gases reflect light differently. So when you look at the giant red spot, for instance, on Jupiter, it just happens to be made up of stuff that reflects more red light or orange light than the white clouds, for instance, okay? Oops, get back there, you. So the equatorial diameter is 142,984 kilometers. So that's way bigger than the Earth. Mass is 318 Earths. Now, the reason it's only 318 Earths in mass is because it's mostly gas, and gas is a lot lighter than rock. So even though it's so much bigger than the Earth, it's just not as heavy as you would think it would be because it's made of gas. It has rings. The surface temperature is minus 108 degrees Celsius. Now, of course, this planet is the planet that we consider the ringed planet, and this is Saturn. Saturn is the most distant planet that can be seen with the naked eye. So when you go out at night, if you know where to look, all the inferior planets and Jupiter, you could actually see. Now, what's really cool, if you look, you don't even need a telescope, you just a pair of binoculars. If you look at, say, Jupiter, for instance, you could actually go out and see the moons. They're called the Galilean moons of Jupiter, 4 moons. And you will see every night the moons will be in a different place because they're constantly rotating. And that's kind of a fun thing to do if you have a pair of binoculars. Every night go out and look at Jupiter. If you're lucky, you got good binoculars, you'll actually be able to see, some of the rings. Might be able to see the red spot if you have a good telescope. But you'll definitely see those. And they were called the Galilean moons is because those are the only moons that Galileo was able to see through his primitive telescope. So he sort of discovered those, okay? Saturn orbits the sun once every 29.4 Earth years. So it takes 29 of our years for 1 year of Saturn to occur. Saturn has the most extensive ring system in the solar system. Saturn's rings are made mostly of chunks of ice and small amount of carbonaceous dust, which means carbon, okay? The rings stretch out more than 120,700 kilometers from the planet, but are amazingly thin. They're only about 20 meters thick. Saturn has 150 moons. So I just want to throw in this little tidbit, guys. Science is not written in stone most of the time. For most things. A long time ago, when I used to work in a hospital kitchen, and the guy who, like one of the supervisors there, he knew I was interested in astronomy. So he gave me a book, an astronomical textbook, college textbook, from 1912. When you look through that book, it'll say that Saturn only has 9 moons. The reason is our technology wasn't good enough to be able to see all the other moons. Now that we could actually go to Saturn, we could actually count the moons more accurately. But back then, imagine you took a test and you said, well, yeah, Saturn has 150 moons. You would have flunked your test. Because, like I said, things in science they change based on our technology and our ability to understand it, okay? So the next planet out from Earth basically looks like a big blob of blue, and that's Uranus. Turns on its axis once every 17 hours and minutes. Oh, I wrote that twice. Uranus hits the coldest temperature of any planet. And I'm not sure if you can see what that is, but I can't see what that is. And actually, Uranus has some rings. So that's 3 planets so far that have rings in our solar system. So Saturn is not the only one. This is Neptune, is the most distant planet from the sun. Remember, Pluto's not a planet anymore. Neptune is the smallest of the gas giants. A year on Neptune lasts 165 Earth years. That means it takes 165 of our Earth years for Neptune to go around the sun one time. Okay. Neptune has 6 faint rings. It spins on its axis very rapidly. And Neptune has 14 moons. Now, even though Pluto is not considered a planet anymore, and I'm going to explain to you why in a second, why they changed that. But this is a photograph, this is an actual photograph of Pluto taken from the spaceship that went out and flew past Pluto. Now from Earth, Pluto just looks like a dot with no features. So nobody really knew what Pluto looked like, and people were amazed. The scientists were amazed when they got there and they saw this picture of Pluto, how incredible it really looked. So Pluto was reclassified from a planet to a dwarf planet in 2006. When the International Astronomical Union formalized the definition of a planet as a planet is a celestial body that A, is in orbit around the sun, which Pluto is, has sufficient mass for its self-gravity to overcome the rigid body forces, so that it's a sphere. If it wasn't big enough to form a sphere, it's definitely not a planet. So all planets are spheres. And it has enough self-gravity to, let's see, past that, C, it's able to clear its neighborhood around its orbit of all debris. So the reason why when the Earth goes around the sun, we're not banging into stuff, is because the mass of the Earth and the gravity of the Earth, anything that was in its path, it already sucked it in and became part of the Earth. Or it flung it out of the way because of the gravity. Well, it turns out that C is the problem for Pluto. It's big enough to be a sphere. It actually goes around the sun, but it doesn't have enough gravity to clear its path around the sun. So there's lots of junk around Pluto. And that's the reason why it's actually considered a dwarf planet, not a regular planet. Now, Pluto has 5 moons, known moons that we know of. Pluto is 1/3 water. And Pluto has an eccentric and inclined orbit, which means instead of in that plane, that ecliptic I talked about, for some reason, maybe it was hit by another planet a long time ago. It got pushed out of that planetary disk, and now goes, instead of going this way, it goes this way around. And sometimes it's actually closer to the Earth than Neptune is, which means it's actually, and so the order of the planets would have changed at certain times of its life. Okay. So I want to show you this other video because us mere humans, it's really hard for us to imagine the size of things in the universe. There are actually a bunch of really good animations on the internet that you could find to show you how the sizes of things relative to each other. So I'm just going to play this, and I just want to show you this really cool thing. We're going to start, I think it starts at the moon, if I'm not mistaken. Okay, let's just jump ahead real quick there. Fireflies. All right, so it starts at the moon. So there's Pluto compared to the size of the Earth's moon, okay? So Mercury is a little bit bigger than our moon. Ganymede, which is it's a Jupiter's moon, is a little bit bigger than Mercury, and so on. That's the size of Mars compared to. So Venus is a little bit smaller than the Earth, but now watch the difference between the Earth, and we don't need to worry about Kepler-1c, even though it's a rocky planet revolving around some other planet of the sun. Here's Neptune, if you could still see Earth on the left-hand side. Uranus is a little bit bigger than Neptune. But now there's Saturn compared to Uranus. This is not part of our solar system. This is a red dwarf star, so disregard that. There's Jupiter. Now there's the sun compared to, think back on the Earth. Now this gets really interesting because try to keep in mind how big the Earth was compared to our sun. Now it's going to show our sun compared to other stars in the universe. Pollux is another star. It's called an orange giant. Arcturus, which is a star that we can see from where we live. Aldebaran's another star that we can see. So I really wish they would be able to show you that in a long chain to see how big that star is compared to the Earth. The Earth is not even the size of a head pin compared to that. It's smaller than, I would say, probably smaller than an atom compared to the size of that sun. So stars do change size based on their age. So some of these red supergiants are at the end of their life cycle. They've enlarged so big that even if there were planets circling around it, it's already engulfed all the planets and so on. So it's mind-boggling, the size of things in our universe. All right, let's see if we can go ahead forward here. How do we get ahead? There. So let's talk about a couple of other things that you find in the universe. Now, we live in a galaxy. We call it the Milky Way galaxy. We can only see parts of the galaxy. Like if we go out in a dark night, especially in the summertime, you could actually see the Milky Way, the strip of the Milky Way going across the sky. That's actually part of the galaxy that we live in. Our galaxy is a spiral galaxy, and we live on one of the spiral arms of that galaxy. Now, obviously, we can't take a picture of our galaxy. So this galaxy right here is called the Andromeda Galaxy. So the other thing I want to talk about besides the size of things are the distances that things are. Things are so far away that instead of using miles or kilometers to find out how far away a galaxy is or a star, we use something called light years. Now, try to wrap your head around this. Light travels at 186,000 miles per second, which means if you snap your fingers, light just traveled 186,000 miles. The distance that light travels in a year at 186,000 miles per second is called the light year. So imagine that. Imagine being able to go 186,000 miles per second and travel at that speed for a whole year. That equals 1 light year. That's over 6 trillion miles. Kind of mind-boggling already, right? So what I want you to understand also is we talked about light before. If something is 1 light year away, it takes 1 year for that light to travel to you and reach your eye. So if you looked at a star that was 1 light year away, you're actually looking at that star where it was 1 year ago. To know where the star is now, you'd have to wait a year because it takes 1 year for the light from that star to reach you. I know it's kind of hard to wrap your head around this, but it gets better. This galaxy that we're looking at right now, the Andromeda Galaxy, is 2,300,000 light years away. It's our closest neighbor. When you look up in the sky, you can actually see this galaxy without a telescope. You can actually see it looks like a little dot, a little fuzz, because it's so close. The light that reaches your eye that allows you to see that galaxy, it traveled 2,300,000 years to reach your eye. So you're actually looking at that galaxy, where it was and what it looked like 2,300,000 years ago. So you're looking back in time. Our galaxy, the Milky Way galaxy, is 100 light years across, which means if you can measure it, it would take you 100,000 light years to get across from one side to the other. So that means if somebody on one side of the galaxy, say, turned on a really bright flashlight, the person at the other end of the galaxy would not see that flashlight turn on for 100,000 years. It would take that long for the light to travel across our galaxy to reach your eye. So imagine what that means, guys. To me, I find this so fascinating because you're looking back in time. Every time you look up in the sky, you're looking back in time. And theoretically, since light has a finite speed, somebody 10 feet away from you, you're looking at them, it took time for the light to get to your eye that reflected off of them, which means everything you look at, you're looking at in the past. The only thing that you would see that's even close to being right now is if you stuck your finger right in your eye like this. The distance is so small that it's negligible. You wouldn't notice the difference. So I don't know if you guys could comprehend what I'm saying, but every time you look at something, you're looking at it in the past. Sometimes in the very short past, or sometimes in the distant past. So, for instance, again, this galaxy. You're looking at that galaxy where it was and what it looks like, or what it looked like 2,300,000 years ago. It took that long for the light from that galaxy to reach your eye. So, you know how people say, like, there's no such thing as time travel? So, I came up with this theory one time, and I think it would probably work if there was a way of actually going fast enough. So the light actually reflects off the Earth. It's constantly reflecting off the Earth, right? If you could travel fast enough out into space, like say 1,000 times faster than the speed of light, and then quickly turn around, you'd actually see the Earth the way it looked in the past. How cool is that? All right, guys, I'm just realizing Chris just told me what time it was, and she's about to start her short stories with Chris. So I'm going to end it here. I know we talked about a lot of things, and a lot of it really takes a lot of thought. But there's so much cool stuff to learn about when it comes to space and our solar system. We only barely touched on it. So I hope you guys, if you have any questions real quick, we could talk. I could try to answer them. If not, we'll see you guys soon, okay? Any questions?
Well, where did Wi-Fi come from?
Where did Wi-Fi come from?
Yeah.
Well, somebody invented it. But of course,
Okay.
the frequency that, let me close this, guys, see if we can get back on here. There we go. Oops. Okay, here we go. So Wi-Fi uses microwaves. Microwaves are part of the electromagnetic spectrum that actually comes from the sun. And we've learned how to make that and use it to transport voice or other things or light. So for instance, when you say you have a radio, you turn that radio on, well, you're not actually sucking in those radio frequencies. Those radio frequencies are always there. We just have no way of grabbing them until we turn on a radio. A radio is made to actually focus in on that radio wave, that frequency, and you're able to hear the radio or TV. All of those things are traveling through the air at all times, including microwaves, unfortunately. So yeah, I don't know what the guy's name was that invented Wi-Fi, but
Okay.
people use it all the time because now everything is wireless.
Because sometimes you can pick up the signal good, and sometimes you can't. That's why I asked.
Yeah, and that has a lot. There's a lot of reasons for that, and one is the company that supplies your Wi-Fi for you. Sometimes if you go on in the evening after dinner, when every kid on the planet, or in North Carolina, or in Chatham County, I should say, is practically on their phone or on their computer, you're not getting as much as the percentage of the bandwidth as you really should be, because it's being shared amongst so many people. So there are certain times of the day where even the quality of my Wi-Fi goes down.
Okay. Thank you.
Sure. All right, guys, I'm going to sign off because Chris is doing her thing, and hopefully you guys get a chance to go